In this video, we will review enthalpy, which is the measure of a total energy of a system. We will also discuss the first law of thermodynamics, which states that energy cannot be created nor destroyed in a chemical or physical process, although energy can be converted from one form to another. To say this another way, the total energy of the universe is a constant. First, let's define some terms we introduced already. What is the universe? It is everything we see around us, and that which we cannot see, but only imagine. Well, for the sake of this chemistry class, there are two parts to every universe. The system is what is being studied. If you are boiling water, the system is the water, and the surroundings are everything else around the system. For our boiling water example, the surroundings are the pot, the oven, and even you. We define the universe by saying that it is the system plus the surroundings. Energy comes into play in this discussion with the first law of thermodynamics, which states that energy must be a constant in the universe, or the change of energy of the universe must equal zero. Since our universe is only made up of two things, this leads to the change of energy of the system plus the change of energy of the surroundings equals the change of energy of the universe, or the change of energy of the system equals negative the change of energy of the surroundings. This change of energy we are referring to is the change in internal energy. The change of internal energy of a chemical system will have three types of molecular motion. If we start our boiling process with solid ice, the ice molecules cannot move very much. In fact, they can only vibrate in place. When we get to liquid water, the molecules can still vibrate, but now they can also translate in space. This means they can flow past each other. And finally, when you get to the gas phase of water, molecules can vibrate, translate, and rotate around in space. This is because gas molecules have no other entities holding them in place, so they can move however they wish. You can change internal energy two different ways. The first way is when a gas pushes against something. A classic example of this is a car piston. When gasoline combusts in your engine, it produces a gas which pushes against the pistons of your engine, causing your engine to run or push your wheels forward. We define this type of change of internal energy as work. In the case of a gas, this work is defined as the negative of the pressure times the change in volume of the gas. The ideal gas law equation is pressure times volume equals the number of moles times the ideal gas law constant times the temperature, or PV equals nRT. Sometimes reactions take place that involve a change in the number of moles of a substance. In this case, work equals the other half of the ideal gas law equation, negative the change in number of moles of gas times the ideal gas law constant times temperature. In physics classes, work is defined as the force an object asserts through a distance. The other way to change internal energy is to either add or remove heat. Back to our boiling water example. In this case, heat from the system is lost when water is boiled. I know this seems counterintuitive to what happens when you boil water. It seems that the system would gain heat. But remember, the system is just the water. So although the pot gains heat, the water loses heat as it boils. The definition of the change in internal energy for a system is the work plus the heat. The signs of these variables are important because work and heat can both be negative or positive. We will draw a diagram to help explain this. In the diagram, the system is represented by a box. Work done on a system is positive work, and work done by the system is negative work. Heat absorbed by the system is positive heat, and heat released by the system is negative heat. Endothermic reactions are one in which the heat is lost by the system and the heat is positive. Exothermic reactions are one in which the heat is gained by the system and the heat is negative. Some questions will try to confuse you with the wording of what is happening in the system. It is best to keep this diagram in your mind when working with problems that utilize this equation. Enthalpy, H, of a system needs to be taken into account when running a reaction at constant pressure. Most reactions are run at constant pressure, including reactions that happen inside your body at atmospheric pressure and reactions that are run in open beakers. Enthalpy is hard to quantify, but change in enthalpy is easy because it equals the heat that is lost or gained by a system at constant pressure. Another equation for enthalpy is related to the equation for internal energy of a system. This equation is change in internal energy equals heat plus work. Our work that we are concerned with in chemical systems is pressure, volume, work, and work equals negative pressure times change in volume. If we substitute in our work term and our enthalpy term into our internal energy equation, we come up with delta E equals change in enthalpy minus pressure times change in volume. If we solve for change in enthalpy, or delta H, this equals delta E plus P times delta V. Enthalpy, internal energy, pressure, volume, and temperature are all state functions. This can be determined because all the variables used to describe these quantities are capital letters. A state function only depends on starting or ending states. It does not matter the path it takes to get there. Work and heat are not state functions. This means that it does matter the path it takes to calculate these quantities. This can be determined because the variables W and Q are lowercase letters. Even though heat is the same as enthalpy, it is the constant pressure that makes the enthalpy a state function, whereas heat is not a state function. Since enthalpy is a state function, there are many ways to calculate change in enthalpy for a reaction that only involves final and initial values, including bond energies, Hess's law, calorimetry, and standard heat of reactions. Now we will work on some problems using the concepts discussed in this video. The change in internal energy for the combustion of 1 mole of methane, CH4, in a cylinder is 892.4 kilojoules. If a piston connected to the cylinder performs 492 kilojoules of expansion work, how much heat is lost from the system? In this equation, they are asking for heat lost from the system, or Q. What kind of information do they give us to find this answer? They give us the change in internal energy equals negative 892.4 kilojoules. They also give us the amount of expansion work that is done on the piston as 492 kilojoules. The equation you need to solve for this answer is delta E equals Q plus W. In this problem, we are looking for Q, so the equation rearranges to Q equals delta E minus W. We know our change in internal energy is negative, but what about our work? Let's go to our diagram of the signs of heat and work to figure this out. Expansion work means that the system is pushing outward and is doing the work on the surrounding, or the work is being done by the system, which corresponds to a negative work. So therefore, our answer is negative 892.4 kilojoules minus negative 492 kilojoules, which equals negative 400.4 kilojoules. Suppose that an electric battery drives an electric motor, and that the battery and the motor are the system. During a certain period, the motor does 555 kilojoules of work, and the motor and the battery release 124 kilojoules of heat into the surroundings, perhaps as a result of friction. What is the delta E of the system? In this question, they are asking you for the change in internal energy of the system. What kind of information do they give you? They give you an amount of work, 555 kilojoules, and an amount of heat, 124 kilojoules. The equation you need to solve for this answer is delta E equals Q plus W. We need to figure out the signs of our heat and our work. Let's go to our diagram of the signs of heat and work to figure this out. Work is being done by the system because the problem states that the motor does 555 kilojoules of work. This corresponds to a negative work, negative 555 kilojoules. The heat is released from the system, and according to the diagram, heat released is negative. So therefore, our answer is negative 124 kilojoules plus negative 555 kilojoules, which equals negative 679 kilojoules. An electric heater operates and absorbs 120,000 joules to heat the gas in a cell. The gas expands from 2.0 to 2.5 liters against an atmospheric pressure of 1.0 atm. What is the change in internal energy of the system in kilojoules? This question again is asking for delta E of the system. What kind of information do they give you to solve this answer? They give you the amount of heat energy that is absorbed to heat the gas at a constant pressure. We know that it is a constant pressure because they state that this is happening against an atmospheric pressure of 1.0 atm. So they have given you the delta H of this reaction, and it is a positive enthalpy because the system absorbed the heat. They have also given you information about the volume and the pressure of the system. The equation we need to use is delta E equals change in enthalpy minus pressure times change in volume. Let us plug what we know into this equation. We know our change in enthalpy term is positive 120,000 joules, and our pressure is 1.0 atm. When we say change in volume, we mean final minus initial volume. The delta symbol always equals final minus initial. Since the gas is expanding, it ends up at 2.5 liters, and it starts at 2.0 liters. So the change in volume is 0.5 liters. Let's look at our units here. We have enthalpy in joules and pressure times change of volume in atm times liter. Our final unit is going to be messed up if we just use these units. To convert these units, use the conversion factor that 101.3 joules equals 1 liter atm. So to convert 1.0 atm times 0.5 liters into joules, we will multiply by 101.3, which equals 50.65 joules. Then, to solve for our final answer, 120,000 joules minus 50.65 joules equals 119,949 joules. Then divide by 1,000 to find our answer in kilojoules, which equals 119.9 kilojoules. Calculate the work that must be done by the reaction at 298 Kelvin to make room for the products for the octane combustion when 2.00 moles of octane is burned via this equation. 2 C8H18 liquid plus 25 O2 gas results in 16 CO2 gas plus 18 H2O gas. In this problem, they are asking for work. Work equals negative P delta V, but they don't give you any information about pressure or volume. Work equals negative change in moles of gas times the ideal gas law constant times the temperature. Remember, a change always equals final minus initial. Our final number of moles of gas are both CO2 and H2O molecules. We have 16 carbon dioxide and 18 waters for a total of 34 moles of gas. Now remember, this work term only includes the moles of gas, so our moles of our liquid octane are not going to be included in our gas moles. Our initial number of moles are the 25 moles of oxygen molecules. So our change in number of gas moles is 34 minus 25, which equals 9 moles of gas. Our ideal gas law constant we are going to use for this equation is 8.314 joules per mole Kelvin, because we want the work to be solved in terms of joules. Our temperature we were given in the problem equals 298 Kelvin, and we want our temperature to be in Kelvin to cancel out with our ideal gas law constant. So therefore, our work equals negative 9 moles times 8.314 joules per mole times Kelvin times 298 Kelvin, which equals negative 22,298 joules. Alternatively, we can divide this answer by 1,000 to get negative 22.3 kilojoules.